Hi everyone, welcome to the continuation of one sample hypothesis testing. Now on to the fun stuff, running hypothesis tests. First we will start with hypothesis testing for the population mean when sigma, the population standard deviation, is known. Here we use a z-test. Please note that it is unusual to know your population standard deviation, and if you do, you probably know your population mean too, and therefore a hypothesis test is unnecessary. In any case, let's work through this example as it will provide a foundation for the t-test. With hypothesis testing, you can use the p-value approach or the critical value approach. You only need to use one of these approaches, however, as they will yield the exact same decision and conclusion. Often students learning this for the first time find it easier to start with the critical value approach, and then they slowly move to the p-value approach, especially for regression analysis. I'll present both methods and leave it up to you which one you choose. The book also discusses a third approach, setting up confidence intervals. In my experience, this is very confusing for students as it involves extra calculations, so I will not discuss this method here, but if it works for you, please feel free to use it instead. Okay, so here we have three different hypothesis tests. On the left we are testing a direction, lower left tail test. The hypotheses may be something like the average wait time at the medical centre is less than 15 minutes. As you can see, the hypotheses relate to this example, and the less than in the alternative hypothesis reveals that it is a lower tail test. In this hypothesis test, we are only testing for the mean being significantly less than 15 minutes, so our alpha of 0.05 or 5% is all in the lower tail, and we will have one cutoff value only. Alternatively, look at the example in the middle. Here we're looking for a difference, and therefore we have a two-tailed test. The hypotheses may be something like the average fill of a bag of potato chips is 80 grams, and the alternative that it is not equal to or different to 80 grams. Here you can see the alpha level is split over the two tails to allow the test to detect a difference significantly greater than or significantly less than 80 grams. The alpha of 5% is therefore split between the two tails, so there is 2.5% in each tail and therefore two cutoff values, one negative and one positive. In the last example on the lower right of the slide, we again see a directional test, but this time it's an upper tail or a right tail test. The hypotheses may be that the tyres last longer than 60,000 kilometres. The alpha of 5% appears in the upper tail only, and there is one cutoff value to reflect this, as the test will only detect a difference significantly above 60,000 kilometres. So now here are 4 steps to hypothesis testing. First, specify the null and alternative hypotheses. Next, determine the test statistic and compute the value. Third, calculate the p-value and make a decision. That is, are we going to reject HO or do not reject HO? Lastly, we draw a conclusion which means we make a decision in relation to the example. Now let's work through an example. Here, an events coordinator wants to determine the average age of attendees at a fundraising event. The events coordinator wants to determine if the average age of attendees is greater than 67 years. The null and alternative hypotheses are presented on the slide. Next, consider what information is known for the exercise. First, the sample size, lowercase n, is 25. The sample mean, x bar, is 71 years, and the population standard deviation, sigma, is known and 9 years. As the standard deviation is known, we calculate a z statistic. This is calculated using the formula on the slide. As you can see, the z statistic is calculated as 2.22. Next, we look up our z tables. A z of 2.22 yields a p-value of 0.9868. But since we want the p-value beyond 2.22, we subtract the p-value from 1 to get a p-value of 0.0132. Have a look at the z distribution on the slide. The hypothesized population mean of 67 is standardized to 0, and the sample mean of 71 is standardized to 2.22. The p-value of 0.0132 is the area to the right of z. Now we are ready to make a decision and a conclusion. As the p-value of 0.0132 is less than our alpha of 0.05, we reject the null hypothesis. Lastly, we conclude that the average age of attendees is greater than 67 years. Now let's consider the critical value approach. With the critical value approach, we determine a critical value that creates a cutoff point and separates the rejection region or regions from the non-rejection region. Again, as with the p-value approach, I'm presenting you 3 different hypothesis tests for each of the different sets of hypotheses. Now please note we find a Z critical value from the Z tables, and if this Z statistic falls into the rejection region, as shown on the slides as the shaded green area or areas for the two-tail test, the null hypothesis is rejected. If the Z statistic falls in the non-rejection region, which is the pinky area on the distributions, the null hypothesis is not rejected. Here we have 4 steps. First we specify the null and alternative hypothesis, then we specify the test and compute the test value. Next we find the critical value or values, and then we make a decision and draw a conclusion. Again, here's the same example. The Z statistic was calculated as 2.22. Next we look up the critical value by looking inside our Z tables. We look at the positive tables as our Z critical is going to be a positive number being in the upper tail and to the right of the hypothesized mean, which is standardized as 0. If you look up 0.9500, because our tables give you the p-value to the left of Z, you'll find that it falls between 1.64 and 1.65. So our Z critical for an upper tail test with an alpha of 5% is 1.645, and this will always be the case. Now we need to place our Z statistic on our Z distribution. As you can see, a value of 2.22 will fall to the right of 1.645 and in our rejection region. Therefore, we reject HO. We conclude that the average age of attendees is greater than 67 years. This conclusion is the same as the conclusion from our p-value approach. So let's bring the critical value approach and the p-value approach together. Here you can see that a Z statistic of 2.22 yields a p-value of 0.0132. The Z critical value of 1.645 is the cutoff point, where only 5% of values fall above this point. Therefore, a Z statistic to the right of the Z critical value will always give a p-value less than 0.05, so your decision using either method will be the same. Okay, so here's another example. It is the back-to-school example from before. Remember our hypotheses related to testing for a difference in that the average spending equals $606.40. Or does not equal $606.40. Now we have sample data for 30 households, so lowercase n equals 30. The sample mean is $622.85. The population standard deviation is given as $65. The Z statistic is then calculated as 1.39. As you can see with the two-tail test, there are 2 rejection regions because we are testing for a difference in that spending may be significantly greater or significantly less than the hypothesized average. The Z critical values are plus or minus 1.96, meaning that 2.5% of the probability is in either tail. You can look up the Z tables to check this. As 1.39 falls in the non-rejection region, we do not reject the null hypothesis. Similarly, we could look up the Z statistic of 1.39, which yields a p-value of 0.0823. We need to multiply this by 2 to account for the two-tailed test. So 0.1649 is greater than alpha of 0.05, so we do not reject the null hypothesis. In conclusion, there is not enough evidence that the average back-to-school spending differs from $606.40. So that you don't have to look up corresponding Z critical values for given alpha levels, here is a table with these values. Now we will move on to t-tests. In most cases, the population standard deviation is unknown and you would run a t-test in place of a z-test. With the t-test, S, the sample standard deviation, replaces sigma, the population standard deviation, when calculating the t-statistic. The t-distribution is actually a family of distributions. For smaller samples, the t-distribution is flatter in the top and fatter in the tails, and as the sample size gets larger, it gets closer in shape to the Z distribution. Here is an example from your book. The research question is to do with university students, on average, studying less than 24 hours per week. As you can see, this research question is reflected in the alternative hypothesis, and the null is the exact opposite. Now assume a random sample of 35 students is selected and the sample mean is 16.37 hours with a standard deviation of 7.22 hours. Please note this is a sample standard deviation, not sigma, the population standard deviation. Next we check the normality assumption. This is assumed through central limit theory, as the sample size is greater than 30. Next, the t-statistic is calculated as negative 6.25. This is the standardised value of 16.37. It will of course be negative, as 16.37 is less than the hypothesised mean of 24. Now we need to look up the t-table at the back of your textbook, Table 2, page 732. This table is different to the z-table. The t-critical values are inside the table, and to find the appropriate t-critical value we need to calculate degrees of freedom. For a one-sample test this is simple, it's the sample size take 1, so 35 take 1 is 34. We look down the first column of the t-table and stop at 34. Then we rule across to the alpha level of 0.05, as this is a one-tail test, with the alpha in the lower tail. If it was a two-tail test, we would look at an alpha of 0.025. The value in the table is 1.691, but we need to make this a negative number as we are testing a one-tail lower tail test. Please note the t-table will only give you positive values, and you need to know when to make these negative. Now for the decision. So since the t-statistic of negative 6.25 is less than the t-critical value of negative 1.691, we reject the null hypothesis. There is enough evidence to conclude that the average number of hours studied per week is less than 24 hours. Okay, so that's one sample hypothesis testing done. Well done.